Hey guys, how's it going? This is Kelly Cox, and instead of calling this one proofs for prime numbers, which I'm not really showing proofs, I'm looking at patterns and creating formulas from the patterns that can be applied to applications to look for primes. And so what I'm going to do is walk you through the way I created the formulas from looking at the patterns, and then show you what those formulas in action can do. So get our slides moving. So the formula pattern, that the main pattern that I look at is a 210 block of numbers. So in every 210 numbers, the prime numbers 2 and 3 eliminate 105 numbers. The next thing is, still looking at 2 and 3. In the remaining 105 numbers, we're going to have the number 6 create these 35 positions, which eliminates those numbers. The prime number 5 in 210 numbers eliminates 14 numbers, and 7 eliminates 8 numbers. That leaves us with 48 possible locations for a prime out of 210 numbers to be in. So these are the only locations that I'm concerned about. Out of those, we can have 6 pairs of twins, right? Side by side twins can happen. So we can have 4 consecutive primes in a row. There are 9 other locations for twins to show up. So we have a total of 15 chances in 210 numbers for a pair of twins to show up. And then we have 18 locations or positions that can be a single prime. So I can write these as 35 positions with an A and B on either side. So A would be 6 minus 1, and B's would be 6 plus 1. So the positions of the side-by-side twins are going to be position 2 and 3, 17, 18, 32, 33. And then the other positions that can be twins are these locations. 35 is a special location. 35B is the starting point for a new pattern to emerge, I would say, right? It has some special things that can happen there. And then the positions that are singles are these positions, and then A's would be minus 1, B's would be plus 1. And here's the rest. So any other place cannot be a prime number, so I'm not going to even, right, with my formula, I'm not going to look at anything but these 35 positions, right, plus or minus 1. So what does that formula actually look like? Right, all the primes can be found by taking 6 times 1 to infinity plus or minus 1. And once you find a prime, each prime eliminates, right, prime times prime, which would be prime squared. It eliminates itself plus any previous primes, right? So prime times prime plus all previous primes for each plus or minus 1 that we find. So what that looks like is 6 times 1 creates 5 and 7. 5 removes 5 times 5. 7 removes 7 times 5 and 7 times 7. Alright, so I don't need to duplicate 5 times 5, 5 times 7, because 7 is going to pick it up. And then 6 times 2, it creates 11 and 13. 5 and 7 don't eliminate those, so 11 would eliminate 11 times 5, 11 times 7, 11 times 11. 13 would remove 13 and 5, 7, 11, and then squared. So it's going to, each prime is going to remove all the primes that it's found plus itself squared. From a position point of view, each prime removes 6 times prime plus or minus prime. So what's that look like? So you take 5, the first prime we found, multiply it by 6, that's 30, and that gives you the triplets that it's going to remove, right? It's removing 5 times 6 is 30, plus or minus 5 would remove 25 and 35. And then I can take that number, multiply it by 2, right? It gets me to 60, and then plus or minus 5, it removes 55 and 65. Multiply it times 3, it's going to take you to 90, and it's going to remove 85 and 95. Right? And this pattern continues to infinity. It removes those three numbers progressively. Right? And then 7 would remove 7 times 6 is 42, plus or minus 7 is 35, 49. And so when you're looking at it this way, you want to remember that 35 is removed by the greater, not the lesser number. So it's removed by 7 and not 5. So let's see. I'm going to show you what does that look like. I'll bring an Excel file into the front. So if I put in the number 1, I can see that 1 times 6 is 6, plus or minus 1 is 5 and 7, 2 times 6 is 12, 11 and 13, right? So here are my prime positions, right? So all of these numbers are the prime positions out here. If I take my first prime, 5, and I put it in here, it's 5. 5 times 5 is going to be the first prime that it eliminates, right? So here's my, if I look at these pink numbers, they are the 5 times 6, and for some reason I managed to make this print. So 5 times 6 is 30, plus or minus 5 is 25, 35. Times 2 is 60, 55, 65. So here are all those numbers, right, times the primes, right? I can see the prime positions out here, right? So 5 times the prime positions eliminates all these numbers. And so I can take any prime and put it in here. So 30031, right? It's a prime, and it's going to eliminate numbers bigger than Excel can tell us. There we go. Alright, so 30,031 times 6 is 180,186 plus or minus 30,031, right? Gives you the first two yellow and green numbers, right? So these are eliminated, right? And if you take the first two primes, 5 times your number you're looking at 7 times, right? This is what they come out to, right? And so these are, right? This is a pattern for eliminating numbers as primes. So as you can see, 25 times 30,031 eliminates this number, right? We can factor it down to 5s if I want to, but I don't need to, right? I just need to stick to this formula to find the primes and the anti-primes, right? So this is kind of the way that the process I go for finding the anti-primes, and then I just go through each 6, right? Then I go back to 1, and then I just look for, right, if I'm looking for the primes between 100 and 200, right, I'm going to start with this 96, 102 would be my first block that I look at, and then I know 101 and 103 are primes, 107, 109, right, these are my prime locations. I'm going to look at all of these, figure out, right, I'm going to take each one of these, so I'm going to take 101, put it in here and say, so 5 times 101, right? So I'm not really going to look at 101 because 101 times 5 is outside the range I'm looking at. So I'm going to start with 5, right? And so I'm going to look at all of these numbers as being anti-primes. So 25, 35, 55. I'm going to eliminate these numbers, and then I'm going to go to 7, right, and follow the same process. So I get to a 6 that is going to give me 6 minus 7 is 203. I'm not concerned about that one, right? So I'm going to only look at the first 4. And then I'm going to go to 11 and look at these numbers. Right. So this is the logic I go through in looking for my non-prime, anti-prime numbers, right? So here's what that map looks like, right? Here's my 35 positions, and then the A and B's. A's are -1, B's are +1. The pink numbers are my positions, which are multiples of 6. Red are the pairs of twins that you can find. So those 4 numbers, right? You can have a maximum of 5 numbers in a row, right? So we can have these 2 sets of twins and then a single tagged on, so it would be 5 primes in a row that you could potentially have. And down here 31, 32, and 33 positions could create a, and then 16, 17, 18, 19 you could have a string of 6 numbers together. But you have all these, right, after you get past 7, go into your next prime, 11. Every one of these new primes is going to create a anti-prime pattern that's going to overlay this. But they'll cycle in and out of this pattern. And then we have refocus. We have our blues, which are twin prime locations. So you have in these multiples of 5 times 6, right? So 30, 60, 90, up to 210. You have 5 potential places to have twins. And 7, 12, 23, and 28. The gray locations are your singles, right? You're never going to have triplets because of the way the 5 eliminates it. So you can never have 3 twins ever again, stacked up, right? You have 5, 7, 11, 13, 17, 19. That's the last time you can have that, because the next set, right, your position 4, 5 times 5 eliminates that from ever happening again. Right, so our yellow locations are primes removed by 5, and then the green ones are removed by 7. So that is your patterns, right, for every 210 numbers. So when I actually throw numbers into this, here's what it looks like. Right, the first 210 numbers, here's the numbers that I'm concerned with. I'm not concerned about any other numbers, right? So 6 times 1 plus or minus 1 is 5 and 7. 6 times 2 is 12. Plus or minus 1 is 11, 13, 17, 18, 23, 25, 29, 31, right? Now if I look at the second, what we need to remember is, right, 35B would be 211. That's the start of a new pattern. And then if I cycle through, I believe 11 of these, I'm going to be back to a new 35B, starting a new cycle. Right, so what does that look like? Let me pull up and get it on the right one. Nothing like doing stuff live. There we go. So here are my prime positions, 1 through 35. So I put in a random number, 419, just to give us the first 2 blocks. Right, so it takes 419, divides it. I'm going to round down Right, dividing that number by 210 gives me this, but because 419 is not in the first 210, I'm looking at the second one, and there's 419. Right, but I can put in any number I want. 950. Right, 950 is not in the rounded down, so it's in the next one. 950 is not a number I'm concerned about, so it's between 948 and 954. Right, but it's not a number that even has a chance of being a prime, so I'm not concerned about it. Right, so it's a factor of 2 or 3. But I can punch in any number and see where it fits into here. Right, so I can immediately know if it's a multiple. I should try a different number. 2, 2, 3. Try that. Right, 9, 2, 2, 3 is in a potential prime location. Right, it also could be a potential twin. Right, so I can check 9221 and 9223 and see if they're primes. Right, but I know I have a higher chance of this number being a prime than 950, right? Just by looking at this pattern. So I know that 2, 3, 6, 5, and 7 are not factors of it per se. If I 953, it is not a prime because 23 times 401 eliminates it. So in the process, if I'm looking at numbers ranging from 9,000 to 10,000, it would be removed when I got to 23. Alright, so this is how I logically look at the pattern. Right, I can quickly use this pattern to see if a number's even worth looking at as a prime. So the rest of how I use the formula is take a random number, divide by 6 gives me the max locations I need to look at. Divide by 5 multiplied by 10 gives me the possible number of primes. Finding all the antiprimes less than the random number is now what I do. So possible primes minus antiprimes plus 2 gives me the number of primes in the random number. So if I take 92 as a random number, divide by 6 is 15. I also use to find the position, right? So if I round down or round up, so I need to know what's left over. So 15 times 6 is 90, so that leaves me 2. So I know I can round down. If it comes up to a 5, I want to round up. Just so 15 divided by 5 is 3. 3 times 10 is 30, so I have a possible total of 30 primes in the number 92. right? The anti-primes are 5 times 5 is 25, 7 would give me 35 and 49, 11 would give me 55, 77, and 21. 21 is greater than that, so I wouldn't, it's eliminated, but it's outside my range, so I don't care about it, right? Any number greater than 92, I don't care. So 13 would eliminate 65 and 91. The other two I don't care about. 17 would give me 85, and 19 would give me 95, which is greater than 92. I don't need to search anymore, right? I can end my searching. It gives me a total of 8 numbers eliminated. And if I take my total primes, minus 8 is 22, plus 2 and 3, which, right, I don't care about those in my calculations. I'm just going to add those at the end, because I'm starting at 5. So 24, total primes less than 92 is 24, and I know what they are, right? Right. Any prime that is killed is still a prime killer. What that means is 5 times 5 is 25. 25 helps eliminate all these numbers, and then it eliminates 625 on its own, 25 to 25, which, you know, if you're factoring, you'd factor that down to 5 times 5 times 5 times 5, right? But I don't need to break down into the factors, because I know 25 is not a prime, but it is a prime killer. And so what I want to do is show you that I'm going to show you my application now. So this one is going to, what I want to do is kind of just cover up what we're looking at. So the example 92, put in 92, and then I say how many primes are in 92. Alright, and it's going to tell me, right, it's going to go through 6 times 1 minus 1 is 5, so I have no non-anti-primes yet, so it's 5 is a prime. But you're going to see, right, it's going to immediately do the calculation. 5 times 5 is an anti-prime, so it's going to put it in the list. The next number is 7. 6 times 1 plus 1 is 7. So 7 is a prime, and it's going to eliminate 35, 49. And the next one is 2 times 6 minus 1 is 11. 11 eliminates 55 and 77. And it's going to 13 is going to eliminate 91. 17 is eliminating 85. 65. 19 is eliminating nothing, right? So then it's just going to say these are primes. Now we get to 25, and it knows it's not a prime because it's in my list of anti-primes. 29 is prime, 31 is prime, 35 is not, 37, 41, 43, 49 is not a prime, 55 is not a prime. Alright, so it's just looking at every possible position between 0 and 92, looking for these, just looking at each location, and right as it's looking at these, it's adding to the non-primes. And now we're done, right? And it found 8 numbers are not prime, 24 are. So it found 22 primes, right? 22 plus 8 is my max primes, 30, right? And I only had to look at 32% of the numbers. I don't need to worry about any prime that I've found greater than 18, right? So 17, right, is our max prime. Alright, and the last position I'm going to look at is 89, 91, because 92 would fall over in the next one. So, right, here's the same thing, except I'm going to not say whether they're prime or not prime, right? I'm not going to pop up the bubble, but we're going to add 9,022, right? How many primes are there up to that number? And so it's going to tell me 5 and 7 are my first primes. As you can see, here's a list of all the numbers, right? There's 1,928 numbers that are not prime, and 1,140 numbers that are prime. So I've put 10,000, right, this one you can really quickly verify, right? There's 1,229, and if you Google it, you'll know that that's the right number. But I also know what these numbers are and what numbers are in prime positions that can't be prime because they're eliminated by the numbers that I'm looking at. So the next thing I did was take this up to the logic of if I start at a specific location and I end at a specific location, how many primes are in those, what are the primes between 10,000 and 20,000? So I click this, right, it's found, right. This one, right, uses the second type of searching, right? It's going to go through 5 times 5, right? It's going to find 5 times a number that equals 10,000 and start there going up the steps, right? So if I look at my prime killer, it's going to do 5, and then it's going to find where, probably not going to go that high, 10,000, right? So it's going to start at 10,020 and start plotting in these numbers, right? All the yellow ones here. And start putting these in. So it's going to start with 5 times 2003 and go till it hits 20,000, right? Eliminating these numbers. So once it's done finding the anti-primes, then it's going to fill in, it's going to go to all those locations and look at, evaluate those individually. So basically, I can take this and start and stop anywhere I want. It's using Visual Basic. But I'll show you, I ran this one so it did 2 million to 4 million. It took like 3 days to find all the anti-primes, non-primes that are in those numbers. Right, there's 5,032,453. Right, and then it started going through each prime. Starting at 2 million, 2,000,003 is a prime, 29 is a prime, 39 is a prime. Right, and it found 1,300 or 134,213 primes, right, between those. And it took 8 hours to find the primes, right, so it started around 9 in the morning and finished around 5. So I started looking for something besides Visual Basic, which is not even a math application, programming language, and I started using R. R is a little bit faster. Here's what R looks like, and there are 1,063,319 non-primes between, I looked at 1 million to 5 million. Right, this took 48 hours to go through 4 million numbers. And what I noticed was that the way that I'm looking for the non-primes, it spent 24 hours cycling through doing nothing. Right, it wasn't adding, so I'm inefficiently looking for non-primes. I'm spending way too much time looking at these numbers. So now I'm going to try and speed up that process. So I'm going to have to figure out the logic that I use to do this. But it found 27,015 primes. And if I look up here, it's telling me here's what they are. It doesn't mean anything in this format, but if I print out print APP, it's going to give me the start of those primes. And then I reached the max. So there were 269,000 that it couldn't print out. But here's the end of them, right? These numbers are primes. And I don't have to question it because it spent more than 24 hours making sure that it found all the antiprimes. And so basically, if we look at this, right, I'm telling it give me a start in number, setting up my counts to 0. And then I take and start manipulating these numbers to find some start and end points. Right, so here I'm looking for, is it in that 5th position? So do I need to add 1? If not, I'm going to round down. So I'm going to round down anyways, but if after rounding down I discover that I'm in that position A, right, which would be a 5, then I'm going to add it back, right, and then I'm going to start my counts, do some more manipulations, and then I'm going to start, I'm going to create my bounds, right, I'm going to look at numbers between 1 million and 5 million. Create my some more counts, and then I'm going to look for non-primes, anti-primes. So it's going to go from 1 to my stopping point, which is 5 million, and it's just going to cycle through 5 times every number between 1 million and 2 million that whatever numbers fall into those categories. And then it's going to do the same for 7. And it's going to do that for my starting position, is a 6 plus or minus, that number. So whatever these first two counts are, it's going to do that for 5 and 7. The A and B positions. So it's going to do all that. It's putting those into my anti-prime, and then I'm just going to cycle through each position that can be a prime and see if it's in the anti-prime. If it's not, then I'm going to add it to my primes. So I can start with any number I want and end at any number I want. So if this was capable of taking the largest prime found, I could put that number as a starting point and end wherever I wanted to, and it would look for non-primes up to that point, from the largest known prime to however far out I want to look. It would find all the non-primes, and then I could look through and see, is there any positions that were not on the list, then they are a prime. And so the only other thing that I would want to say is Euler's infinite prime. He basically says, or how everybody explains it is, if I take all the primes, add 1 to it, that will be a new prime. And what I would have to say about that is that if you take the first 2 primes, multiply them together, 2 times 3 is 6, plus 1 is 7, that is a prime, but we skipped a prime, Number 5 was skipped in finding this new prime. And then if I add that prime to it, 5, I get 30 plus 1, it's a prime, but I skipped 27 primes in this process. So I add another one, 7, 210, which is the last pattern that stays, that I build my search pattern off of. But looking at it, 210 plus 1, 211 is a prime. And so I made the assumption at this point that without knowing what people were saying about the infinite primes, it was my assumption that if I keep just adding the next prime, so if I add another one, 11, 323, 2,310 plus 1 is 2311, it is a prime, but we skipped 23,500 primes to look at this. But it's a prime. Now, the next one, I add the next prime, 13 is 30,030, prime skipped is 3,242. this is where this logic ends, because if I take those, I add 1 to it, it's 30,031, which is not a prime, because 2 primes that we skipped multiply to be that. So the logic in saying if I take all these primes, add them together, you're skipping primes. There's no way to add all the primes together, because other patterns, right, are going to start coming in and destroying, right, whatever patterns you're looking at. You can't add all the primes together because you're going to skip. Right, if I just take the first 10 primes, I'm in the 6.5 billion range. So the way Euler's, right, they say Euler's discovered that there are infinite primes. I just disagree that that logic holds true, because the first 2 primes you multiply together, you're already skipping primes. So there's no way to keep putting those together, because you take the first 6 primes, 2 through 13, put them together, you skip 32,000 plus primes, and 2 of those, right, that are not part of the formula, right, are eliminating that plus 1. And so the higher you go, you have just, you're adding, right, that's 3,242 patterns that aren't being accounted for when I do a plus 1. And so you're going to almost infinity patterns really quick, right? You're going to infinity your patterns before you infinity your primes. And I think I want to show you, let me find it, I'm pretty sure it's in here. Yeah. Just real quick, when I think about the prime number 5, right, in every 10 numbers, 2 are eliminated by this prime. So 20% of prime positions are eliminated by the number 5. In every 14, so 1/5. Every 14 numbers, 7 eliminates 2. So 1/7 of numbers are eliminated out of every 14. 11 is 2 22nds, or 1/11 of primes are removed by 11. Right, 1/11 of the numbers are removed by 11 out of every 22 numbers. 13 is 26 numbers, so 1/13. Right, so these percentages are dropping very quickly. So if we go down to the 100th prime, which is 227, right, out of every 454 numbers, 2 are eliminated, which is, right, this number here, right, less than 1/2 of 1%, right, but it's 1 over 227. So there should be some way to take and create a formula for how many numbers, up to whatever you're looking at, right? I can take all these numbers and do a calculation and know, right, that in 454 numbers, all of these are going to play an impact on us. But again, right, 7 times 5, 11 times 5, 11 times 7, you have these duplicates happening. But these duplicates they don't show up till it's like 5 times 7 times 11, right? So this is the latest thing that I'm working on for the primes, right? How can I find this, instead of looking at the natural log to say this is a rough estimate, right? This should give you a better look at how many primes are in a given number. So I'm trying to, I guess, create this to be something that I can use to quickly know what percentage of numbers are going to be prime. Right. These are the accuracy, right? You can't get more accurate than this. And I guess I'll end there. And thank you for watching this video.